docking orbit, then injected on a translunar trajectory. A burn of the service module propulsion system, and a plane change that placed the spacecraft into the proper orbit for lunar landing. The landing was performed in the lunar module. After the landing and exploration of the lunar surface, the lunar module was launched on the surface of the moon and rendezvoused with the orbiting command module. With the rendezvous completed, the space vehicle is now preparing for trans-Earth injection and drag. The basic problem is to bring the spacecraft crew from the moon to a specific landing site on Earth. To see how this is accomplished, we must first look at the Earth-Moon geometry. The moon is revolving around the Earth. The Earth is rotating on its axis. Each of these motions has a specific effect on the spacecraft's ability to reach the landing site. To examine these effects and how they act on the return and entry trajectory, we must first define the antipode. The line is drawn from the center of the moon through the center of the Earth, penetrating the Earth's surface, which faces away from the moon. The point of penetration is called the antipode, which means simply the point opposite. The return trajectory will pass over the antipode being determined at the time the spacecraft leaves the moon's vicinity. The distance from the point of entry into the atmosphere to the antipode is relatively fixed. The entry range limits of the spacecraft are also fixed so that landing occurs near the antipode. Therefore, the landing area is defined, and the target point can be selected within this area. The recovery forces are, of course, located on the surface of the Earth and rotating with it, while the trajectory is fixed. By selecting the proper trajectory can vary the transit time of the spacecraft up to 24 hours. In order to bring the spacecraft to the longitude of the recovery forces, it is only necessary to control the return time of the spacecraft to the Earth, while the Earth is into the proper position. This gives us complete freedom of choice as to selection of the landing longitude. The landing longitude, then, can be selected with operational constraints in mind, such as a required landing on water, location of land masses, convenience of recovery force placement, and so forth. The other geometric constraint is the latitude at which the spacecraft will land. The primary factor influencing the latitude is the inclination of the moon. To understand this, we must again look at the Earth-Moon geometry. As the moon revolves around the Earth, the plane described by the lunar orbit is called the moon orbit plane. The moon orbit plane is inclined to the Earth's equatorial. As the moon moves around the Earth, it changes its position relative to the Earth's equator. The angle between the equatorial plane and the Earth-Moon line is called the angle of declination. This angle varies from a maximum when the moon is here to 0 degrees when the moon is here. The return trajectory begins at the moon and must pass over the antipode. This means that the plane of the return trajectory must contain the Earth-Moon line. The injection burn to start the lunar spacecraft on its return trip will also fix the plane of the return trajectory. This plane can be rotated around the Earth-Moon line. The limits of this rotation are determined operationally. This range of planes, along with the entry range limits, determines the range of latitudes that can be achieved. Because of the relatively short entry range, and thus the small distance from the antipode to the target point, it can be seen that the latitude range is quite small. The landing latitude selected within this range is essentially fixed at time of trans-Earth injection. While latitude range is determined by the possible range of return trajectory planes and the entry range, the location of the latitude range is determined by the declination of the moon. As the moon changes its declination throughout the month, the latitude range shifts accordingly across the surface of the Earth. In review, we have seen that accurate control of the landing longitude can be achieved by varying the transit time of the returning spacecraft until the Earth and recovery forces have rotated to the desired position. The range of landing latitudes is determined by range return trajectory planes and the entry range. The position of this band of landing latitudes, on the other hand, is relatively fixed by the declination of the moon at the time of trans-Earth injection. Thus, control of landing latitudes is extremely limited. To understand how the entry trajectory is shaped, it is necessary to understand the conditions existing at entry. The spacecraft will enter the upper limit of the atmosphere at an altitude of 400,000 feet. This altitude is, by definition, where the perceptible atmosphere of Earth is first encountered. It will enter at a speed of approximately 4,500 miles per hour. This is a speed considerably greater than that required to put the spacecraft in circular orbit around the Earth. This means that if we take away the atmosphere, the spacecraft would approach the Earth and arrive at a point called the vacuum perigee altitude. This would be the point of closest approach of the trans-Earth trajectory if Earth had no atmosphere. Since the velocity of the spacecraft is greater than the velocity required to achieve circular orbit, the momentum of the spacecraft would cause it to move away from the Earth after passing the point of closest approach. But Earth does have an atmosphere. The vacuum perigee altitude is located well below the limit of the perceptible atmosphere. If the spacecraft could be controlled to precisely the correct flight path angle, capture could occur as a result of atmospheric drag on the spacecraft. However, if the spacecraft relied only on drag, the corridor would be too narrow to guarantee a safe return. To see why this is, let's take a closer look. To achieve a safe capture and entry using only atmospheric drag, the spacecraft trajectory cannot exceed very narrow limits. That is, it must arrive within a given distance of the nominal vacuum perigee altitude. This can be related directly to the angle at which the spacecraft enters the atmosphere. This range of flight paths is called the entry corridor. If the spacecraft enters at an angle shallower than that of the upper or overshoot limit of the corridor, it will skip off the atmosphere like a flat stone off a pond of water and go into an orbit that will not allow it to re-enter until its oxygen and power are exhausted. If the spacecraft should enter at an angle steeper than the lower or undershoot limit, the high G-force dissolved would incapacitate the crew and could exceed the spacecraft's heat structural capacities and cause it to burn up like a meteor. Therefore, to achieve safe entry, the spacecraft must follow a trajectory within the entry corridor. However, with limitations of hardware and trajectory design over translunar distances and velocities, it is impossible to control the trajectory to guarantee an approach closer than this to the nominal vacuum perigee altitude. Since this is directly related to the entry corridor, it can be seen that if atmospheric drag alone is used as a controlling factor, it is impossible to guarantee a safe entry. Therefore, aerodynamic lift is used to assist the drag force and widen the corridor to acceptable limits. The aerodynamic characteristics of the entry vehicle or command module play a decisive role in the Apollo atmospheric entry phase, especially since even after the corridor is achieved, future errors could result in disaster. We will look at this later. Now let's see how this lift is generated. The Apollo command module is basically conical in shape. It will enter the atmosphere blunt end forward. As it does so, it will strike molecules of air. According to Newton's first law, a particle at rest or in motion tends to stay at rest or in uniform motion in a straight line until acted upon by an outside force. The spacecraft provides this force, deflecting particles of air. According to Newton's third law, to every action there is an equal and opposite reaction. Then, just as the air is acted upon by a force from the spacecraft, the air imparts a force on the spacecraft of equal magnitude, but in the opposite direction. This line represents the symmetrical center line of the command module. If the center of gravity were located on this axis of symmetry, then all air striking the end would be deflected equally in all directions. This means that the aerodynamic forces of the deflection perpendicular to the axis of symmetry would be balanced. Then the only effect of the interaction of the spacecraft and the particles of air would be along the axis of symmetry and opposite to the direction of the spacecraft motion. Therefore, the only aerodynamic force acting on the spacecraft would be in a direction opposite the direction of spacecraft motion. This force is called drag. If, however, the center of gravity is shifted off the center line, a new set of spins occurs. The spacecraft now realigns itself according to the shift in the center of gravity. This new alignment is a stable trim attitude. That is, if the spacecraft should deviate from this attitude, aerodynamic forces will tend to restore it to this position. Now, the air strikes the spacecraft more on one side of the center of gravity than the other. Again, the spacecraft behaves according to Newton's laws. More air is deflected downward. Thus, a lifting force is created on the spacecraft. The center of gravity is fixed relative to the spacecraft. By rolling the spacecraft about its center of gravity, the direction of lift can be changed and aerodynamic control achieved. We can now see how this affects the limits of the entry corridor. If the entry angle is steep, a lift-up attitude can be held to bring the spacecraft onto a safe entry path. If the angle is shallow, lift-down can achieve a safe entry. Therefore, the entry range or entry corridor is expanded. The spacecraft must be controlled to arrive within slightly plus or minus 15 miles of the desired vacuum pitch altitude. This is a return trajectory of over 250,000 miles. We have seen what does the entry corridor, its overshoot and unshoot limits. How aerodynamic control of the command module is achieved by rolling it around its offset center of gravity, thus changing the direction of lift. And this increases the depth of the entry corridor. We are now ready to see what happens to the command module during the phase. Since the spacecraft left the moon's vicinity, it has been falling to Earth for 3.5 days, over a distance of about 250,000 miles. Before actually entering the atmosphere, the service module, which contains the primary system and all but a very limited oxygen and power supply, will be jettisoned. This is roughly analogous to a scuba diver taking off his air tanks before starting up from the bottom of the sea and holding his breath all the way to the surface. Once the command module enters the atmosphere, it has about 1,000 miles and a bit over 2.5 minutes of controllability, divided into 2 brief control periods. Most of this controllability will be used up during the first control period. The trajectory the command module will follow is basically as follows. It will enter on a given flight path and proceed downward to the pull-up point. Just before pull-up, it enters the atmosphere dense enough to allow aerodynamic control of its landing point and begins its first control period. The command module will then climb until it skips out of this denser atmosphere. The skip is primarily to increase the maximum range of the spacecraft and to reduce the aerodynamic heating load on the heat shield. As the skip is approached, aerodynamic control is reduced to practically zero. During the skip, the crew will be experiencing weightlessness. The skip will not take the command module beyond the 400,000 foot level. It will then descend, starting at second entry, and go on to the second control period. The entry phase is terminated at 23,500 foot level, at which point the drogue chutes are deployed, and the spacecraft is committed to its landing point. We will now examine the entry trajectory in detail and see what each portion. As the command module enters the fringe of the atmosphere at 400,000 feet, there will be as yet no aerodynamic control. At this point, the command module will be aligned to its stable trim attitude. It should be noted that there are 2 stable trim attitudes. The desired one is blunt end forward. The other is rivet forward. Since each shield is on the blunt end, this entry alignment would be disastrous. Proper alignment of the spacecraft is determined by the onboard computer from data received from the tracking network prior to entry. After proper alignment, there will be control only in the roll axis, pitch and yaw being stabilized by aerodynamic forces. At the 0.05 G mark, the point at which deceleration can be sensed for the first time, limited aerodynamic stabilization of the spacecraft will be evident. The spacecraft will be in a lift-up attitude, which, in the nominal case, will be maintained until the first control period. When the 2 to 2.5 G region is reached, capture is so highly probable as to be considered achieved. The spacecraft continues in a lift attitude until it enters the dense portion of the atmosphere. Just before pull-up, maximum G loads will be placed on the spacecraft. Just before this, the first control period begins. During the first 70 seconds of this control period, any error or failure to correct an error could result in what is called, in great understatement, a non-recoverable situation. That is, too much lift-up could put the spacecraft and crew into an orbit that would last beyond the lifetime of the command module systems. Too much lift-down could take the spacecraft and crew beyond the stress and heat rate limits and result in destruction of the command module. As the spacecraft approaches the skip, the aerodynamic forces become less and approach zero, so aerodynamic control approaches zero. It is during this first control period a real determination of where the spacecraft will land is made. To understand this, take a look at a flat map of the Earth. This point represents the target, that is, the point at which the spacecraft should land. This is the landing footprint, or area in which the spacecraft might land, at the beginning of the first control period. The usable portion of this footprint is designed to compensate for accrued errors and to provide alternate landing sites in case of bad weather. Of this total footprint, only 1,000 nautical miles or 1,150 statute miles are usable. During the first 70 seconds, the first control period, the spacecraft must be maneuvered so that this 20,700 mile footprint shrinks around the target to this footprint about 2,070 miles long. 90% of the maneuverability is used up during this period. This 70 seconds, then, is the critical period of the entry phase. During the remainder of the first control period until the skip, the landing footprint will reduce to this area, about 690 miles long. Only minor adjustments of the trajectory can be made as the skip is approached. If all goes well during the first control period, the spacecraft and crew should be on a trajectory that can be safely controlled during the second entry. We are now ready to look at the skip and the final part of the entry phase. During the skip, the crew will ride along and monitor the trajectory. Will have no control over it. However, the command module will be aligned to its trim position in preparation for the second entry. As in the first entry, aerodynamic stabilization begins at the 0.05 G mark. The spacecraft must be properly aligned by this point. The second control period, beginning at 0.2 Gs, will last a minute and a half. While a dangerous skip-out cannot occur, an error could take the spacecraft and crew beyond the stress limits. It is this second control period that the fine-tuning of the entry trajectory takes place. That is, the spacecraft will be maneuvered to shrink the landing footprint as determined during the first control period, so that the spacecraft will arrive at the target. The Apollo entry phase will terminate at about 23,500 feet altitude. At this altitude, the drogue chutes will come out, and the spacecraft descend to splashdown by parachute. Reviewing now, we see that before entering the atmosphere, the service module containing all at the entry oxygen and power supplies will be jettisoned, and the command module position its trim alignment. It enters the atmosphere at the 400,000-foot level. At 0.05 G, aerodynamic stabilization begins. At the 2 to 2.5 G level, capture is considered achieved. The command module continues on the trajectory until pull-up for the controlled skip maneuver. This is where maximum G loads will be placed on the spacecraft and crew. Just before pull-up, the first control period will begin. During the first critical 70 seconds of this control period, the initial landing footprint, 20,700 miles in length, will be shrunk around the target to this 2,070-mile footprint. In the remainder of this first control period, the footprint will shrink further to this 690-mile long area. The first control period is followed by the controlled skip. During the skip, the command module will be aligned for the second entry. The second control period begins at 0.2 Gs and lasts about 1.5 minutes. During this period, the trajectory will be tuned to bring the command module down on the target. The Apollo atmospheric entry phase terminates at an altitude of 23,500 feet with the opening of the drogue. We have seen how the landing area on Earth is by the time of travel from the Moon, the declination of the Moon relative to the Earth's equatorial plane, and the plane of the trans-Earth trajectory. We have seen how the entry corridor is defined, how aerodynamic control of the command module is achieved by rolling it about set center of gravity, and we have followed the spacecraft and crew through the entry trajectory. Just how important the atmospheric entry phase of the lunar mission is can be highlighted by the fact that while it is one of the briefest phases, it requires one of the largest onboard programs. Once the spacecraft is in the atmosphere, things happen fast, and there is little time for corrections as compared with earlier portions of the mission. For instance, an error made during the critical 71st control period could cause a high-speed skip, resulting in placing the command module and crew into a trajectory that exhausts the oxygen and power supply before landing. Yet during this period, communication blackout exists between the ground and the spacecraft, caused by the ionization of the air from the heat of entry. Therefore, entry will be entirely controlled through onboard computations. Just before the entry phase, the ground will transmit the necessary data to the spacecraft. That data being where you are, where you're going, where you want to go. we have presented the major factors affecting the atmospheric entry phase of the manned lunar mission. It requires careful planning to assure the safe return to Earth of spacecraft and crew. And this is the final part of an overall plan, a plan designed to carry us safely to the moon and back.